Next, let's consider lower bound on R3T. So as I mentioned before, 1995, Jung and Kim proved that this is at least some constant times n square over log t. And this on Hiboros and Griffith and Morris, and independently by Bowman and Hibbas, show that this holds with a better constant. So the connection is weird. Okay. The boss of this group, is something called the triangle free process. How do you do it? You start from n isolated vertices and then you add an edge. And you add the next edge, next edge, next edge. While you're doing that, you randomly add an edge, but under the condition that the adding edge does not create any triangle. For example, if this is your graph, maybe let's make it simple. Then how many choices are there? So there are these 4 choices does not create a triangle, while these 3 choices create a triangle. So out of these 4 choices, you choose one of them with probability 1 over 4. And other these choices are forbidden, so those we don't add. We keep do that, and then we can ask a question that this is a random process. So with high probability, when does it end? And then at the end, we will get a maximal triangle free graph. It's not maximum, but it's maximal. So adding edge, you cannot add further edges. Maybe the number of edges is not maximum, but that will create some So, there are some connection issue between my iPad and the computer. Anyway, and they analyze this, then show that this process does not end until this point. So we will obtain a triangle free graph with at least this many edges and no large independence. Anyway, that was roughly how they proved this. And recently there was a breakthrough by breakthrough by Matthews and Verstraete in 2024 proved lower bound for W number R440. They show that this is some constant times, at least some constant times T cube over log to the 4 of T. And this is tied up to this logarithmic vector. The upper bound by attached Komros and Semoredi provides an upper bound, and then this is tied up to this logarithmic vector. So what we want to do is we want to prove, our goal is to prove this is at least, say, some constant times t squared over log cube t. And the proof I will present today is by Yuval Wigderson. And this is in his lecture note. And roughly, the proof idea comes from the two results. Colon's result. Colon in 2017 showed that the existence of triangle-free pseudo-random graph with many edges. And also, Matthews and Brastrade disprove. So using those ideas, the Yuval Wigderson, he reproved this weaker bound with the weaker log term. So this log term is weaker than here, but this proof is simpler. So these proofs are quite complicated, but this provides a lower bound in a simple way with a slightly worse log factor. So roughly speaking, this is what we will do. We will find C4 free and C6 free. The graph that scores at least 8 bipartite graph with many edges. And once we have this bipartite graph, what we will do is that for each vertex here, you have neighborhood. In this neighborhood, we will partition it into two in random way. Then we put the edges with it. So random, complete bipartite graph. And show that this is triangle free. This is because the original graph was C6 free. So if there isn't this edge, that means in the original graph, you could go and come here, right? So if there is a triangle here, then you will see that it will correspond to the C6 in the original graph, but there was no such thing. So this is the K3 free, and this has many edges. And because we randomly put this complete bipartite graph, we will show that this is also locally dense. Then, as this is locally dense, the graph container lemma says that it doesn't have many independents. We can find the upper bound, the number of large independents. And then what we do is we take a random sample. So we choose some random vertices and with the right size. And then in there, we make sure that it doesn't contain any of the independents at a certain size. And this graph will be triangle free and does not contain any independents at a certain size too. That will give us the lower bound. So that's what we want to do, right? We want to construct a graph which is triangle free and then does not contain a t-vertex independent set, and then the number of vertices is realistic. So that's roughly what we will do. And here the reason why it was triangle free was that you find the bipartite graph is this property. So C6 is a subdivision of K3. So here subdivision means that you replace every vertex by path of length 2. And luckily, the proof of them here is similar. They find the C4 free and subdivision of K4. K4 subdivision free. So This is the subdivision of K4. That's related to something called Onan's configuration. And they have a similar, rough sketch. Okay, so instead of going through their one, let's consider this simpler one. So we consider field FQ and a vector space FQ to D3. And in here, you have points. So let P be the or set of all points in this vector space FQ to D3. And the set of all. And let L be the set of all lines in FQ of 3 of the specific form, which is x plus w times 1, y squared. So the direction vector has specific form. For some y, it is 1, y squared. Then what? The number of lines is q cubed. Why? There are q choices for y. And then q to the 3 choices of x. So there are q to the 4 choices of these. But in each line, it has q points. So there are this many choices, and there are q choices, which gives us the same line. So we have to divide by q. So there are many lines. And also the p, the number of points is cube. So let G prime be the incident graph, meaning that this is the bipartite graph between P and L, where point P and then line L are adjacent if P belongs to L. And what we can show is that this G prime does not have C4 or C6. It has curves at least 8. So non-C4 is easy. Two lines have 1 point in common. Say at least at most 1 point in common. Technically it's actually 1 point. So, if you have a C4 and two lines have intersection here, P1 and P2, they have intersection at these 2 points, which is contradiction. So it doesn't have C4. And if this G prime has C6, then what? And you have P1, P2, P3, L1, L2, L3. You have this, right? Then what do you know? If Li is what? Xi plus W times 1, yi square to this form, right? So if P1 and P2 both belong to L1, then what do you know? P1 minus P2 is Wi times y 1, yi square, or some is I a1. This holds. Then P2 minus P3 is W2 times 1, y2, y2 square. And P3 minus P1 should be also W3, 1, y3, y3 square for some wi and then y. So add them, then this is 0. But what do we know? We know that these 3 vectors you know that they are linearly independent. If all yi are different. And this is from the, this matrix 1, 1, 1, y1, y2, y3, y1 square, y2 square, y3 square. This is called the Vandermonde matrix. Vandermonde matrix. And we know that its determinant is same as the multiplication of these 3. So if they are all different, its determinant is non-zero. So this is linearly independent. But what does this mean? That means, y1 is y2 without loss of generality. So 2 lines are parallel. So, yeah. So that means that this cannot be C6. So this shows that G prime has no C4 and then no C6. Now we consider our graph G. So let G be the random graph that's obtained from the following. So for each P, we pick by partition the A of P and B of P of the neighborhood of P in this G prime, which is chosen uniformly and random. So it's P here, it has neighborhoods, so lots of lines here. For each line, we add it to either to here or here with probability half independently and random. Then the resulting graph G is the vertex that is the line. Then we know that this G is triangle free. Why? If there is triangle, if here L1, L2, L3, then what? Then let's say, okay, and I didn't say this. We pick a uniformly random, if AP and BP, and we add all edges between them. We add all edges between AP and BP. And label this edge as P. So this edge is coming from P. Then each edge has unique label. Why? Because this is C4 free. If you have a L1 and L2, and then this comes from P, and then this also comes from P prime, then you have C4 in the original value of G prime, so which is contradiction. Each has a unique label. Okay, let's say you have a triangle here, then say this is P1, and then P2, P3. So each has these three labels. And they all come from, different label. Why? If all of them are different, then that give you C6. If all Pi different, then C6 in G prime. We get the C6 in G prime is if contradiction. So P1 equal to P2. In such a case, so this then say P3 is also same with me. Then it's contradiction as we added complete biparticle, which is no triangle in complete biparticle. But if P1 and P2 are same and then P3 are different, then what? All these three come from P1 and the other two come from P3. Again, we have a simple. So in G prime. In any case, this G is triangle free. Okay. So next what? We want to show that the G is locally dense. We can claim that with high probability, for every vertex set X, which is subset of L, will size at least a 200 Q square log Q. The number of edges in X is at least X square over 20. But this is, we prove this because we want to apply graph container lemma. So how do we do it? So we fix one such X. We first count the number S of pairs L1, L2 in both are in X that lies in some neighborhood of P, so that it has some possibility to be common edge. Okay. Once we compute this, then probably half of these pairs will become edges. So half of them will be the expected number of edges in X. So we want to first compute the expected number of edges in X, and then show some concentration result, like Chernobyl we did before, show that with high probability, it's very close to the expectation. So we get the bound. Then how do you compute this? For each P, what? You count the intersection size between X and this neighborhood of P. And you take the square because we are counting the pairs. Then Cauchy-Schwarz says that you take the 1 over the number in P, and you take the summation m square. So this is a lower bound. But from double counting, what's this? So you have P, and then you have L, you have here P, F. So for each one, you see how many edges are going there. That's exactly what this is counting. But from this perspective, that's also counting the edges from X and P. And that's same as the summing the degrees of vertices here in G prime. So this is just the summation of all the degrees in X, the lines in X. And then you add them, and then you take the square. This is what we know. In G prime, every line contains exactly Q coins. So this G prime is Q regular. So what? P has Q cube vertices, and this is Q times X square, and this is at least X size of X over Q. So we know this is the pairs, number of pairs that lies in some neighborhood of some vertex, some point P in G prime. Now let G is the number of edges in here with the random variable counting edges of G in X. Okay, so now we want to apply some concentration results like Chernobyl. But the situation is a bit different from Chernobyl. So this G is summation of, lots of things. So for, say, for each PL, not this way, okay? In each X, for each pair, you can actually get the, say, L and L prime. You can consider this indicator random variable, which is 1 if this is matched, which is 0 if this is not 1. Then, this G is summation of this, all of this. But we cannot apply Chernobyl because those random variables are not independent. For example, we know that there is an edge here, there is an edge here, and we know for sure that there are no edges here. Because this being edge or not depends on the choice of this AP and BP. And there are lots of edges are actually depending on this choice. So once we choose this, many edges are determined so that those events, for those edges, these random variables are not independent. So instead, we can use something else as follows. So for each P and L, which are edges in G prime, so P belongs to the line L, we let G LP be the random variable taking value 1 if L is in AP and 0 if L is in BP. And what we know is this G is some function of this value. So we don't know how exactly, this function is. We can write it, but it's quite complicated. But once these are all determined, then G is determined, which we know. Moreover, this function f is Lipschitz in the sense that the following words. Once you have two instances, and then you just change one, everything else is same, but one, we change the value from 0 to 1 or 1 to 0. Then the value here is changes, and that change is bounded. And this, say, L sub LP is what? It's the intersection size of this GP and X. We know that. So for this P, you have a neighborhood, and then this is X. And this is what we know. And if we change this LP, so this is L, then this could be in A or B. That might change the edges here, or it could simply disappear. So the edges inside of here, which is incident to L, might change. So maximum change possibly is this size. And note that we are interested in summation of square of this. You will see why soon. And that's exactly what we computed here, which is F over Q. And moreover, the linearity of expectation is, we don't need the independency or anything. So L and L prime are both in X. The probability that L and L prime are the edges of G is what? So here we are counting different parts instead of a pair. So we can say half times P and L prime half. This is like quarter times all those. Sorry, what did I write wrong? So this is the square. And this is also X square. And then out of this whole pair, L comma L, there is no chance of having edges on same vertex. There are no loops, so you have to subtract it. So this is what? At least X over 5Q. Yeah. Okay, we know that. Now we use the following tool from probability. Let's say we have independent random variable. Taking values from 0 and 1. And if whatever function we have is Li Lipschitz on its ith component, ith coordinate. And G is a function of these. Then say the probability that G is smaller than half times its expectation is bounded by e to the negative expectation square divided by 2 times the summation of Li square. So this concentration lemma, if you can use it, so now we know this, then this expectation, and by this lemma, we know that the probability of this G being smaller than half of the expectation It's at most expectation of minus size of x squared or divided by 50 cube. So this is for specific x. So we take union bound over all choices. So there are cube many lines, and then you choose x many of them, choices of x. The probability that at least one of them so all of them, okay, at least one of them has two less edges or stump x is at most what you consider. So this was the size of x. You choose cube and you choose the size and you take the computation. Then what? If is like the most the expectation of 3 log q minus x squared divided by 50q to the x, and the summation are here. And no matter what f is, x is at least this much. So you can simply say that this is upper bounded by that. And instead of x, you plug in 200 q square log q and 200 q square log q. That you do the computation. Then you see that this is little one as q growth. So this is more than one in particular. That means, with large probability or with positive probability, this holds. Now, we have locally dense conditions, so we can apply the graph container. Let R be this number, 200 times q squared log q, and beta is 1 over 10q. So that's what this is like half times beta times x squared. And say R is like 10q times log q. Then you can check that the graph container lemma, conditions for graph container lemma holds. Okay. Maybe let's go back and check the graph container lemma. This is cube, and this is divided by cube. So R is 200 q squared log q. So this is bigger than that. So all the condition hold. So we can apply the graph container lemma. to conclude that the number of independent set of size k is at most q cube choose r times r choose k minus r, and you can check that this is at most 50q divided by log q to the k. Here, for any k between, say, 30q log q square and q square, this one holds. Okay? Is it? Yeah, it is. From here, we can say that okay, we can actually say that the number of independent set of size and most k is what? For small number, you just add everything. And for large number, you okay, actually it's at least r sake. So we can actually bound the number of independent set of size and most k. So what? Now let's say big N is 200q over log q and n is q cube. So now we pick a subset d prime of L of size n over m, uniformly random. Then what? For a fixed independent set, I of size t, let's say t is 1 over 50 q times log square q. The problem is that it is in E prime with probability, but n minus t choose m minus t divided by n choose m. So that's the probability that I is there. So fixing I, and then this is the number of ways to choose next. And this is what? N over m times n over m minus 1, n over n minus t divided by n minus 1, n minus t plus 1. So this is simple computation, and this is smaller than 1 over m to the t. It is m to the k. Then what? By union bound, the probability that this g d prime contains independent set of size. This is strict. T is less than what? Then many independent set of size T. So this one. And probability is this. So this is strictly less than 1. Thus, what does it say? There exists a choice of P prime such that in here, this is an Q square log Q over 200 vertex set. Vertex triangle free graph with containing no independent set of size T. Then size T is what? This. And what's this? This is what? T square divided by Q log 3T times some constant. So this shows that this holds. Of course, for specific PT, you have to choose your Q in correct way, and you get this lower bound. So this provides the lower bound as we want to. Okay, then. Yeah, thank you for listening. Then I will see you in next video.